What if everything you thought you knew about the universe was just the tip of the iceberg? We live in a reality where time isn't always constant, space isn't always flat, and the rules of physics as we know them can bend or even break. This isn't science fiction, it's the frontier of modern physics. From wormholes that could act as cosmic shortcuts to the idea that time itself might loop back on itself, the theories surrounding space-time distortions are as fascinating as they are mind-bending. These concepts don't just challenge our understanding of the cosmos, they open the door to possibilities that could redefine reality itself. In this video, we're diving deep into the revolutionary ideas that are reshaping how we see the universe, exploring the science behind these mind-blowing theories and what they could mean for the future of humanity. Get ready to question everything you thought you knew about space, time, and the nature of existence. At the heart of our modern understanding of the universe lies a revolutionary idea. Space and time are not separate entities but intertwined into a single, dynamic fabric known as space-time. This groundbreaking concept was introduced by Albert Einstein in his theory of general relativity, a masterpiece of scientific thought that reshaped how we perceive the cosmos. Einstein proposed that massive objects like stars, planets, and even galaxies don't just sit passively in space. They actively warp the very fabric of space-time around them. This warping is what we experience as gravity. Picture it like placing a bowling ball on a trampoline. The ball creates a dent in the surface, and any smaller objects nearby will roll toward it. In the same way, a massive star bends space-time, pulling planets and other objects into its gravitational grip. But Einstein's theory didn't stop there. It also predicted some of the most extraordinary phenomena in the universe, like black holes, regions of space where gravity is so intense that not even light can escape. These cosmic enigmas are essentially extreme distortions of space-time, where the fabric bends so much that it tears a hole in the very structure of reality. And then there are gravitational waves, ripples in space-time caused by cataclysmic events like colliding black holes or neutron stars. These waves, first detected in 2015, confirmed Einstein's predictions and opened a new window into observing the universe. Einstein's work didn't just explain gravity, it gave us the tools to explore the wildest corners of the cosmos. It set the stage for physicists to ask even bigger questions. What if space-time isn't just warped but can be twisted, folded, or even torn? What if the rules we thought were absolute are just the beginning? Today, scientists are building on Einstein's foundation, pushing the boundaries of what we know and venturing into realms that once seemed like pure science fiction. From wormholes to time loops, the journey into the mysteries of space-time is just getting started. Imagine stepping into a tunnel that could instantly transport you to a galaxy millions of light years away. This isn't the plot of a sci-fi movie, it's the tantalizing possibility of wormholes, cosmic shortcuts that could bend the rules of space and time. Wormholes, also known as Einstein-Rosen bridges, are theoretical passages that emerge from solutions to Einstein's equations of general relativity. They suggest that space-time could be folded, creating a bridge between two distant points in the universe. Think of it like folding a piece of paper. If you bring 2 points together and punch a hole through them, you've created a shortcut. In the same way, a wormhole could allow us to traverse vast cosmic distances in the blink of an eye. But here's the catch: wormholes aren't exactly easy to create or maintain. According to the math, these tunnels would require something called exotic matter, a hypothetical substance with negative energy. Unlike the matter we encounter in our everyday lives, exotic matter would have the bizarre ability to repel gravity rather than attract it. This repulsion would be necessary to keep the wormhole stable and prevent it from collapsing the moment it forms. Without it, the tunnel would snap shut faster than you could say interstellar travel. Scientists haven't yet discovered exotic matter, but its existence is a key piece of the wormhole puzzle. Even if we could stabilize a wormhole, the journey through one would be unlike anything we've ever experienced. Picture this: you enter a shimmering portal surrounded by swirling distortions of light and color. The walls of the tunnel might ripple and warp as you move, bending the fabric of space-time around you. Time itself could behave strangely, slowing down or speeding up depending on the conditions inside the wormhole. And then, in what feels like an instant, you emerge on the other side, light years away from where you started. It's a breathtaking idea, but one that comes with countless challenges and unknowns. The implications of wormholes go far beyond just faster than light travel. If they exist, they could also connect not just distant points in space, but different moments in time. This raises mind-bending questions about causality. Could traveling through a wormhole allow us to visit the past or the future? And if so, what would that mean for the fundamental laws of physics? These questions bring us to the edge of what we know and hint at even stranger possibilities waiting to be uncovered. As we explore the mysteries of wormholes, we're not just pushing the boundaries of science, we're reimagining the very nature of reality itself. What if you could step into a world where time itself bends to the rules of speed and gravity? This isn't just a thought experiment, it's a real phenomenon called time dilation, a mind-bending consequence of Einstein's theory of relativity. Time dilation tells us that time isn't a constant, unchanging force. It's fluid, stretching and contracting depending on how fast you're moving or how strong the gravitational pull is around you. For example, astronauts aboard the International Space Station experience time slightly slower than we do here on Earth. Over months in orbit, the difference is tiny, just a fraction of a second, but it's measurable. Their clocks tick a little slower because they're moving at incredible speeds and are farther from Earth's gravity. It's a subtle effect, but it's a reminder that time isn't as rigid as it feels. One of the most famous illustrations of time dilation is the twin paradox. Imagine two identical twins. One stays on Earth while the other travels through space at close to the speed of light. When the traveling twin returns, they'll find that less time has passed for them compared to their sibling on Earth. The spacefaring twin might only have aged a few years, while decades could have gone by back home. This isn't just a theoretical idea, it's been experimentally verified. Scientists have used incredibly precise atomic clocks to measure time dilation. In one famous experiment, clocks were placed on airplanes and flown around the world. When compared to clocks that stayed on the ground, the ones in motion showed a tiny but measurable difference in time. These experiments confirm what Einstein predicted. Time is relative, not absolute. But what does this mean for the future of space travel? As we venture farther into the cosmos, time dilation could become a significant factor. Imagine a spacecraft traveling at a significant fraction of the speed of light. For the astronauts on board, a journey to a distant star might feel like a few years, but back on Earth, centuries could pass. This raises profound questions about how we might one day explore the universe. Could humanity spread across the stars, only to return to a home planet that has moved on without them? And what about extreme environments like the intense gravitational fields near black holes? There, time dilation becomes even more dramatic. An observer watching someone fall toward a black hole would see their clock slow to a crawl, while the person falling would feel time passing normally. It's a strange and haunting idea, but it's grounded in the same science that keeps GPS satellites accurate. Time dilation doesn't just challenge our understanding of time, it hints at even deeper mysteries. If time can stretch and warp, what does that mean for the nature of reality itself? Could time be just one dimension in a much larger, more complex structure? These questions take us beyond Einstein's theories and into the realm of quantum physics and string theory, where the very fabric of space-time might be woven together in ways we're only beginning to comprehend. As we explore these ideas, we're not just learning about the universe, we're redefining what it means to exist within it. What if you could travel back in time and meet your younger self, or even change the course of history? This isn't just a fantasy, it's a concept that emerges from the equations of general relativity. Enter closed time-like curves, hypothetical pathways through space-time that loop back on themselves, creating the possibility of time travel to the past. These curves aren't just science fiction, they're grounded in the same physics that describes black holes and wormholes. In certain solutions to Einstein's equations, like those around a rapidly rotating black hole, space-time can twist so dramatically that it forms a loop. If you were to follow this loop, you could theoretically end up back at a point in your own past, creating a time loop. But time loops aren't as simple as they sound. They come with a host of paradoxes that make physicists scratch their heads. Take the infamous grandfather paradox. If you traveled back in time and somehow prevented your grandfather from meeting your grandmother, you would never have been born. But if you were never born, how could you have traveled back in time in the first place? This kind of logical contradiction is just one of the many headaches that closed time-like curves introduce. They force us to confront questions about free will, determinism, and the very nature of cause and effect. To make sense of these paradoxes, scientists have proposed some fascinating solutions. One idea is the Novikov self-consistency principle, which suggests that any actions taken in the past must be consistent with the timeline that already exists. In other words, you couldn't change the past in a way that creates a contradiction. You might try to prevent your grandparents from meeting, but something would always intervene to ensure their meeting still happens. It's as if the universe has a built-in safety mechanism to prevent paradoxes. Another theory involves the idea of parallel universes, where every possible outcome of a time travel event creates a new branching timeline. In this scenario, you might change the past, but you'd simply create a new reality rather than altering your own. The implications of closed time-like curves go far beyond just time travel. They challenge our understanding of causality itself, the idea that causes must always come before effects. If time loops are possible, then cause and effect could become tangled in ways that defy our everyday experience. Imagine a universe where an event in the future could influence the past, creating a feedback loop that reshapes reality. It's a dizzying thought, but one that pushes the boundaries of what we know about the nature of time. These ideas aren't just theoretical musings, they're grounded in the math of general relativity, which has already proven remarkably accurate in describing the universe. Yet, they also take us into uncharted territory where the rules of physics as we know them might break down. As we explore the possibilities of closed time-like curves, we're not just asking whether time travel is possible, we're reimagining the very fabric of reality and what it means to exist within it. The journey into these mysteries is far from over, and each new discovery brings us closer to understanding the true nature of time itself. As we peel back the layers of space-time, we find ourselves stepping into the bizarre world of quantum mechanics, a realm where particles can be intimately connected across unimaginable distances, defying everything we thought we knew about space and time. This phenomenon is called quantum entanglement, and it's so strange that even Einstein famously referred to it as spooky action at a distance. Picture two particles separated by billions of light years, yet somehow linked in such a way that measuring one instantly affects the other. It's as if they're whispering secrets to each other faster than the speed of light, violating the very rules of classical physics. But here's the kicker, this isn't just a theoretical idea. It's been proven in countless experiments, leaving scientists both amazed and baffled. So, how does entanglement work? Let's break it down. Imagine you have a pair of entangled particles, like two coins that are mysteriously linked. If you flip one coin and it lands on heads, the other will instantly show tails, no matter how far apart they are. This connection happens instantaneously without any signal traveling between them. It's as if the particles share a hidden bond that transcends space and time. But here's where it gets even stranger. This connection doesn't depend on distance. Whether the particles are a millimeter apart or separated by the width of the universe, the result is the same. This challenges one of the core principles of classical physics, that nothing can travel faster than light. Yet, entanglement suggests that information can somehow bypass this cosmic speed limit. Recent experiments have pushed the boundaries of our understanding even further. In a groundbreaking study, scientists used entangled particles to test the limits of this spooky action. They found that the entanglement effect holds true even when the particles are separated by distances so vast that light itself would take significant time to travel between them. This has led some researchers to propose that entanglement might not just be a quirk of quantum mechanics, it could be deeply tied to the very fabric of space-time. Some theories suggest that entangled particles are connected through hidden dimensions, or that space-time itself emerges from a deeper, quantum-level reality. This idea has profound implications for unifying quantum mechanics with Einstein's theory of relativity, two frameworks that have long resisted being merged. One of the most exciting possibilities is that entanglement could be the key to understanding quantum gravity, a theory that would explain how gravity works at the smallest scales. Currently, general relativity describes the universe on a cosmic scale, while quantum mechanics governs the subatomic world. But the two don't play well together, and scientists have been searching for a way to reconcile them. Entanglement might provide the missing link. Some researchers believe that space-time itself could be a kind of hologram, with all the information about the universe encoded on its boundaries. In this view, entanglement might be the threads that weave this holographic reality together, connecting every point in space-time in a vast, intricate web. The implications of this are staggering. If entanglement is truly tied to the structure of space-time, it could revolutionize our understanding of the universe. It might explain how black holes store information, how the Big Bang unfolded, or even how multiple universes could exist alongside our own. But perhaps the most intriguing idea is that entanglement could help bridge the gap between quantum mechanics and relativity, leading to a unified theory of everything. This would be one of the greatest scientific achievements in history, unlocking secrets about the cosmos that we can barely imagine. As we explore the mysteries of quantum entanglement, we're not just uncovering new facts about the universe, we're redefining the very nature of reality. It's a journey that takes us from the smallest particles to the vast expanse of space-time, showing us that the cosmos is far more interconnected than we ever realized. And as we continue to probe these deep questions, we're reminded that the universe is full of surprises, waiting for us to uncover them. The story of entanglement is far from over, and each discovery brings us closer to understanding the true fabric of existence. What if the entire universe, every star, every planet, and every atom, could be described as a kind of cosmic projection, like a hologram? This isn't just a wild idea. It's the essence of the holographic principle, a revolutionary theory that suggests all the information contained within a volume of space can be encoded on its boundary. Imagine looking at a three-dimensional hologram on a flat surface. The image appears to pop out, full of depth and detail, but all the information needed to create it is stored on that two-dimensional surface. The holographic principle proposes something similar for the universe, that everything we see and experience might be encoded on a distant, two-dimensional boundary, like a cosmic projector screen. This theory didn't emerge from thin air. It grew out of the study of black holes, those mysterious regions of space where gravity is so intense that nothing can escape. When scientists began to grapple with the paradox of what happens to information that falls into a black hole, they stumbled upon a startling realization. If information can't be destroyed, a fundamental rule of quantum mechanics, then it must somehow be preserved, even as it vanishes into the black hole's depths. The solution: the information might be encoded on the black hole's event horizon, the boundary beyond which nothing can escape. This led to the idea that the entire universe could work the same way, with all the information about its contents encoded on its outer edges. But how does this connect to space-time? The holographic principle challenges our traditional view of space-time as a smooth, continuous fabric. Instead, it suggests that space-time might be emergent, a kind of illusion created by the interactions of quantum information on a deeper, two-dimensional surface. Think of it like a movie. What we see on the screen is a seamless flow of images, but in reality, it's made up of individual frames. Similarly, the three-dimensional universe we experience might emerge from a more fundamental, two-dimensional reality. This idea has profound implications for unifying quantum mechanics and general relativity, two frameworks that have long resisted being reconciled. The potential of the holographic principle doesn't stop at theoretical physics. It could redefine our understanding of reality itself. If the universe is a kind of hologram, then the boundaries between objects, between space and time, and even between cause and effect might be far more fluid than we thought. It raises questions about the nature of existence. Are we living in a simulation? Is the universe a vast, interconnected web of information? And what does this mean for our place within it? As we explore the holographic principle, we're not just pushing the boundaries of science, we're reimagining the very fabric of reality. It's a journey that takes us from the depths of black holes to the edges of the cosmos, challenging us to see the universe in a completely new way. The holographic principle isn't just a theory. It's a window into a deeper understanding of existence, one that could transform how we see ourselves and the world around us. And as we continue to probe its mysteries, we're reminded that the universe is far stranger and more interconnected than we ever imagined. What if the boundary of a black hole wasn't just a quiet, invisible threshold but a raging inferno? This is the startling idea behind the black hole firewall paradox, a concept that has sparked heated debates among physicists. Traditionally, the event horizon, the point of no return around a black hole, has been thought of as a calm, uneventful place. According to Einstein's general relativity, crossing the event horizon would be uneventful. You wouldn't even notice it happening. But the firewall theory turns this notion on its head, suggesting that the event horizon might instead be a blazing wall of energy, incinerating anything that comes near it. Imagine approaching a black hole, expecting to slip silently into the void, only to encounter a cosmic inferno hotter than a supernova. It's a dramatic and unsettling idea, one that challenges our understanding of black holes and the very fabric of space-time. So, where did this fiery paradox come from? It all ties back to one of the most perplexing questions in physics. What happens to information that falls into a black hole? Quantum mechanics tells us that information can never be destroyed, but black holes seem to defy this rule. When matter crosses the event horizon, it's lost to the outside universe, seemingly taking its information with it. To resolve this contradiction, physicists proposed the idea of Hawking radiation, a process where black holes slowly emit energy and particles, theoretically preserving information. But this solution created a new problem. If Hawking radiation carries away information, the event horizon must become a chaotic, high-energy zone to maintain the balance. And thus, the firewall paradox was born. The implications of this theory are profound. If firewalls exist, they would fundamentally alter our understanding of black holes and space-time. Instead of being smooth, continuous structures, black holes might have violent, turbulent boundaries that tear apart anything that approaches. This not only challenges Einstein's predictions, but also raises questions about the nature of reality itself. Could space-time have hidden layers or boundaries we've yet to comprehend? And what would this mean for the fate of objects or even people venturing too close to a black hole? These questions push the boundaries of both quantum mechanics and general relativity, forcing physicists to rethink some of their most deeply held assumptions. The debate over firewalls is far from settled. Some scientists argue that firewalls are a necessary consequence of preserving information, while others believe they violate the principles of general relativity. It's a clash of ideas that highlights the tension between quantum mechanics and Einstein's theory, two frameworks that have yet to be fully reconciled. This ongoing debate isn't just academic, it's a quest to uncover the true nature of black holes and, by extension, the universe itself. Black holes serve as cosmic laboratories, testing grounds for radical theories that could reshape our understanding of reality. As we explore the mysteries of black holes, we're not just uncovering new facts about the cosmos, we're confronting the limits of our knowledge. The firewall paradox reminds us that the universe is far stranger and more complex than we often assume. And as physicists continue to grapple with these questions, they're not just studying black holes. They're peering into the heart of existence itself, searching for answers that could redefine our place in the universe. Picture a cosmic phenomenon so strange that it flips everything we know about black holes on its head. Instead of pulling in matter and light with an unstoppable gravitational grip, this mysterious object does the exact opposite. It spews out energy and matter into the universe. This is the mind-bending concept of white holes, the theoretical reverse of black holes. While black holes are known for their insatiable appetite, white holes are their polar opposites, acting as cosmic fountains that refuse to let anything in. They're not just a quirky idea, they emerge as valid solutions to Einstein's equations of general relativity, the same math that predicts black holes. But here's the catch: no one has ever observed a white hole, and their existence remains one of the most tantalizing what-ifs in modern physics. So how do white holes work? Imagine a black hole running in reverse. Instead of matter and energy being sucked in, they're violently expelled, as if the universe itself is pushing them out. The equations suggest that if a white hole were to exist, it would be a region of space-time where nothing could enter, but everything could escape. It's like a one-way cosmic door, except the door only swings outward. Some scientists speculate that white holes could even be the other end of a wormhole, with black holes acting as the entrance and white holes as the exit. In this scenario, matter swallowed by a black hole might re-emerge somewhere else in the universe, ejected from a white hole. It's a fascinating idea, but one that comes with a mountain of unanswered questions. One of the biggest challenges with white holes is that they seem to violate one of the most fundamental principles of physics, the second law of thermodynamics, which states that entropy, or disorder, always increases over time. A white hole, by definition, would decrease entropy, effectively reversing the natural flow of the universe. This makes them highly speculative, and many physicists argue that they're more of a mathematical curiosity than a real phenomenon. But that hasn't stopped researchers from exploring their potential role in the cosmos. Some theories suggest that white holes could be the remnants of collapsed black holes, bursting back into existence in a dramatic cosmic rebirth. Others propose that they might be linked to the Big Bang, acting as the explosive engines that fueled the birth of our universe. The idea of white holes also ties into broader questions about the nature of space-time. If they exist, they could provide a glimpse into how the fabric of the universe might be stitched together, connecting distant regions through wormholes or even offering a window into alternate realities. They might also help us understand the mysterious singularity at the heart of black holes, where the laws of physics as we know them break down. By studying white holes, we're not just exploring a theoretical oddity, we're pushing the boundaries of our understanding of space, time, and the very structure of reality. As we venture deeper into the mysteries of white holes, we're reminded of how much we still have to learn about the universe. These cosmic enigmas challenge us to think beyond the familiar, to imagine a cosmos filled with phenomena that defy our everyday experience. Whether white holes exist or not, they inspire us to keep asking questions, to keep exploring, and to keep marveling at the endless possibilities hidden within the fabric of space-time. The journey to uncover their secrets is far from over, and each new discovery brings us closer to understanding the true nature of the universe we call home. What if our universe is just one thread in a vast cosmic tapestry, woven together with countless other universes, each with its own unique rules and realities? This is the essence of the multiverse theory, a mind-expanding idea that suggests our universe might be one of many, perhaps even an infinite number existing alongside it. Imagine a bubbling foam where each bubble represents a separate universe floating in an endless sea of possibilities. Some bubbles might be similar to ours, with stars, galaxies, and life as we know it. Others could be wildly different, governed by entirely different laws of physics, where time flows backward, gravity pushes instead of pulls, or matter takes on forms we can't even imagine. The idea of a multiverse isn't just science fiction. It's grounded in some of the most cutting-edge theories in physics. One of the key pieces of evidence comes from cosmic inflation, the rapid expansion of the universe that occurred just moments after the Big Bang. According to this theory, inflation didn't just happen once. It could have happened countless times, creating pocket universes that exist independently of one another. Each of these universes might have its own unique set of physical constants, like the strength of gravity or the charge of an electron. This means that while our universe has the right conditions for life to emerge, others might be barren or filled with phenomena we can't even begin to comprehend. Quantum mechanics adds another layer to this cosmic puzzle. In the quantum world, particles exist in a haze of probabilities, and every possible outcome of an event might play out in some form. This has led some scientists to propose that every decision, every event creates a branching path, spawning new universes with each possible outcome. Think of it like a tree with infinite branches where every choice you make or don't make creates a new reality. It's a dizzying idea, but one that suggests the multiverse might be far more complex and interconnected than we ever imagined. But how do these parallel realities interact, if at all? Some theories suggest that collisions between universes could leave behind traces in the cosmic microwave background, the faint afterglow of the Big Bang. These imprints might appear as strange patterns or anomalies, like ripples on the surface of a pond. While we haven't definitively detected such evidence yet, the search is ongoing, and the possibility of finding proof of other universes is one of the most exciting frontiers in modern cosmology. The multiverse theory doesn't just challenge our understanding of space and time, it forces us to rethink our place in the cosmos. If there are infinite universes, each with its own version of reality, what does that mean for us? Are we just one of countless versions of ourselves, living out different lives in different worlds? And if so, what connects these realities, if anything? These questions take us to the edge of what we know, into a realm where science and imagination intertwine. As we explore the multiverse, we're not just uncovering new facts about the universe, we're reimagining the very nature of existence. It's a journey that takes us from the tiniest particles to the vast expanse of space-time, showing us that the cosmos is far more interconnected and mysterious than we ever realized. And as we continue to probe these deep questions, we're reminded that the universe is full of surprises, waiting for us to uncover them. The story of the multiverse is far from over, and each discovery brings us closer to understanding the true fabric of reality. What if the universe was stitched together by invisible threads, so thin yet so dense that they could slice through space-time itself? These are cosmic strings, hypothetical one-dimensional defects that could have formed in the fiery aftermath of the Big Bang. Imagine the early universe as a bubbling cauldron, cooling rapidly as it expanded. In that chaotic process, tiny cracks might have formed in the fabric of space-time, leaving behind ultra-thin filaments of unimaginable density. These cosmic strings are thought to be no wider than a proton but stretch across billions of light years, carrying the echoes of the universe's birth. Cosmic strings aren't just fascinating relics of the early universe, they could have profound effects on the cosmos we see today. One of the most striking possibilities is their ability to bend light, a phenomenon known as gravitational lensing. Picture a cosmic string passing between us and a distant galaxy. The string's immense gravitational pull would warp space-time, acting like a magnifying glass and distorting the galaxy's image. This effect could create double images of the same object or even produce bizarre, ring-like structures in the sky. While we haven't definitively detected cosmic strings yet, astronomers are constantly searching for these telltale signs in the light from distant stars and galaxies. But the influence of cosmic strings might go even further. They could have played a role in shaping the large-scale structure of the universe. In the early cosmos, these filaments might have acted like cosmic scaffolding, guiding the formation of galaxies and galaxy clusters. As they moved through space, cosmic strings could have created ripples in the cosmic microwave background, the faint afterglow of the Big Bang. These ripples would be like fingerprints, unique signatures left behind by the string's passage. Detecting such patterns could provide crucial evidence for their existence and help us piece together the story of how the universe evolved. The idea of cosmic strings also connects to other exotic phenomena in physics. For instance, they might be linked to the mysterious dark energy driving the universe's accelerated expansion. Some theories suggest that cosmic strings could decay over time, releasing energy that influences the fabric of space-time. Others propose that they might interact with black holes or even serve as cosmic highways, connecting distant parts of the universe in ways we're only beginning to understand. What makes cosmic strings so captivating is their potential to bridge the gap between the universe's earliest moments and its current state. They remind us that the cosmos is a dynamic, ever-changing place, filled with structures and forces that defy our everyday experience. As we search for these elusive threads, we're not just exploring the origins of space and time, we're uncovering the hidden architecture of reality itself. The hunt for cosmic strings is a journey into the unknown, one that could reveal secrets about the universe that we've only begun to imagine. What if the Big Bang wasn't the beginning of everything, but just one moment in an endless cosmic dance? This is the essence of the Big Bounce theory, a radical idea that paints the universe not as a one-time explosion, but as part of an infinite cycle of expansion and contraction. Picture the universe as a cosmic heartbeat, pulsing outward and inward in a rhythm that repeats over and over again. Instead of a single, dramatic beginning, the Big Bounce suggests that our universe might have been born from the collapse of a previous one, and that its eventual collapse could give rise to yet another. It's a vision of the cosmos that challenges the traditional Big Bang model and opens the door to a universe without a true beginning or end. At the heart of the Big Bounce theory is the idea of avoiding singularities, those points of infinite density and zero volume that mark the Big Bang and the centers of black holes. In the traditional model, the Big Bang starts from a singularity, a state where the laws of physics as we know them break down. But the Big Bounce offers an alternative. Instead of collapsing into a singularity, the universe reaches a point where quantum gravity effects take over. Quantum gravity, a still theoretical framework, could prevent the universe from collapsing all the way to zero size, instead causing it to bounce back into expansion. Think of it like a rubber ball hitting the ground. Instead of flattening into nothingness, it rebounds, launching the cycle anew. One of the most intriguing pieces of evidence for the Big Bounce comes from the study of quantum gravity. In the early universe, when everything was compressed into an incredibly small space, quantum effects would have dominated. These effects could have acted like a cushion, preventing the universe from collapsing into a singularity and instead allowing it to rebound. Some researchers have even suggested that traces of this quantum bounce might be found in the cosmic microwave background, the faint afterglow of the early universe. These imprints, if detected, could provide a smoking gun for the Big Bounce theory, offering a glimpse into the universe's cyclical nature. The implications of the Big Bounce are profound. If the universe is cyclic, then the Big Bang wasn't a one-time event but part of an eternal rhythm. It means that every ending could lead to a new beginning, and that the universe might have no true start or finish. This challenges our traditional notions of time and space, suggesting that the cosmos is far more dynamic and interconnected than we've ever imagined. It also raises questions about what happened in previous cycles. Were there other universes before ours, and will there be others after? And if so, how much like our universe were they, or could they have been completely different? The Big Bounce doesn't just redefine the universe's past, it reshapes our understanding of its future. In a cyclic universe, the end isn't a cold, dark fade into nothingness but a transition into something new. It's a vision of the cosmos that's both awe-inspiring and humbling, reminding us that the universe is full of surprises waiting to be uncovered. As we explore the mysteries of the Big Bounce, we're not just learning about the universe, we're discovering a story that stretches across eternity, a cosmic rhythm that pulses through the very fabric of reality. And with each new discovery, we're reminded that the universe is far more vast, complex, and beautiful than we ever imagined. Why does time always seem to flow in one direction? You've never seen a shattered glass spontaneously reassemble, or a cup of coffee grow hotter as it sits on the table. These everyday experiences point to a fundamental truth about the universe. Time has a direction, an arrow that points from the past to the future. But why is this the case? What gives time its one-way street? The answer lies in one of the most profound principles in physics, the second law of thermodynamics, which tells us that entropy or disorder always increases over time. Think of entropy as a measure of chaos. In a closed system like the universe, things naturally tend to move from order to disorder. A deck of cards starts neatly organized, but shuffle it, and it becomes a jumbled mess. The same principle applies to the cosmos. As time moves forward, entropy increases, and this irreversible process gives time its arrow. It's why we remember the past but not the future, why we age, and why the universe evolves in a way that feels so familiar. But what if we could reverse this process? Could time ever flow backward? The idea of reversing time's arrow isn't just a sci-fi fantasy. It's a question that has intrigued physicists for decades. Imagine a universe where entropy decreases instead of increases. In this world, shattered glasses would spontaneously reassemble, and heat would flow from cold objects to hot ones. It sounds bizarre, but according to the laws of physics, it's not impossible, just incredibly unlikely. The equations of physics are symmetric with respect to time, meaning they work just as well whether time runs forward or backward. Yet, in practice, we never see this happen. The reason lies in probability. A universe moving toward lower entropy is statistically possible, but the odds are so astronomically low that it's effectively impossible. This asymmetry of time raises fascinating questions about the nature of the universe. Why did the universe start in such an ordered state with low entropy to begin with? Some scientists suggest that the Big Bang set the initial conditions for time's arrow, creating a universe that was highly ordered and has been evolving toward greater disorder ever since. Others propose that the arrow of time might be linked to the expansion of the universe itself. As the cosmos expands, it creates more space for entropy to increase, effectively driving time forward. This connection between time and the universe's growth hints at a deeper, more fundamental relationship between space, time, and the laws of physics. But what does this mean for the future of the universe? If entropy is always increasing, will the cosmos eventually reach a state of maximum disorder where nothing can change anymore? This bleak scenario, known as the heat death of the universe, is one possible fate. Yet it also invites us to think about the bigger picture. Is the arrow of time an inevitable feature of the universe, or could it change under different conditions? Could there be regions of the cosmos where time flows differently or even backward? These questions push us to the edge of our understanding, challenging us to rethink what time really is and how it shapes our reality. As we explore the mysteries of the arrow of time, we're not just uncovering the rules that govern the universe, we're unraveling the very fabric of existence. Time isn't just a backdrop to the cosmos, it's a dynamic force deeply intertwined with the laws of physics and the evolution of the universe. And as we continue to probe these deep questions, we're reminded that the cosmos is far more intricate and interconnected than we ever imagined. The story of time is still being written, and each discovery brings us closer to understanding the true nature of the universe we call home. What if empty space wasn't really empty at all? What if, even in the purest vacuum, there's a hidden energy, a subtle force at work that defies our everyday experience? This is the essence of the Casimir Effect, a strange and fascinating quantum phenomenon that reveals the true nature of the vacuum. Picture two uncharged metal plates placed incredibly close together in a vacuum. According to classical physics, nothing should happen, no force, no interaction. But in the quantum world, something extraordinary occurs. The plates are drawn together by an invisible force, as if tiny springs were pulling them closer. This is the Casimir Effect, and it's one of the most striking demonstrations that empty space is anything but empty. So, what's really happening here? To understand the Casimir Effect, we need to dive into the bizarre world of quantum mechanics. In the quantum realm, even a perfect vacuum isn't truly empty. Instead, it's a seething, bubbling sea of virtual particles that constantly pop in and out of existence. These fleeting particles are a consequence of the uncertainty principle, which allows energy to briefly fluctuate, creating pairs of particles and antiparticles that vanish almost as quickly as they appear. Normally, these fluctuations balance out, leaving no observable effect. But when two plates are brought very close together, something changes. The space between the plates restricts the types of fluctuations that can occur, while the space outside the plates remains unaffected. This imbalance creates a pressure difference, and the plates are pushed together by the force of the vacuum itself. The implications of this effect are profound. It demonstrates that the vacuum isn't just an empty void. It's a dynamic, energetic medium filled with quantum activity. This discovery has reshaped our understanding of space and energy, showing that even in the absence of matter, the universe is far from inert. The Casimir Effect also provides a tangible link to the concept of vacuum energy, a form of energy that permeates all of space. Some theories suggest that this vacuum energy could be connected to dark energy, the mysterious force driving the accelerated expansion of the universe. If true, it would mean that the Casimir effect isn't just a curious quantum quirk, it's a window into the fundamental forces shaping the cosmos. But the Casimir effect doesn't just connect to cosmology, it also has implications for our understanding of quantum gravity. Gravity, as described by Einstein's general relativity, operates on the largest scales while quantum mechanics governs the smallest. The challenge of unifying these two frameworks has been one of the greatest puzzles in modern physics. The Casimir effect, with its direct link to vacuum energy, offers a potential clue. It suggests that the fabric of space-time itself might be woven from these quantum fluctuations, hinting at a deeper connection between the quantum world and the structure of the universe. To visualize this, think of space-time as a vast, shimmering fabric. On the largest scales, it appears smooth and continuous, but zoom in, and you'll see it's made up of countless tiny threads, quantum fluctuations that twist and weave together. The Casimir effect is like a tug on those threads, revealing the hidden structure beneath the surface. It's a reminder that even the most familiar aspects of the universe, like the vacuum of space, are filled with complex, dynamic processes that we're only beginning to understand. As we explore the mysteries of the Casimir effect, we're not just uncovering new facts about the quantum world, we're peering into the very fabric of reality. It's a journey that takes us from the tiniest scales of existence to the vast expanse of the cosmos, showing us that the universe is far more interconnected and mysterious than we ever imagined. And with each discovery, we're reminded that the cosmos is full of surprises, waiting for us to uncover them. The story of the Casimir effect is far from over, and each new insight brings us closer to understanding the true nature of the universe we call home. What if we could travel faster than light, not by breaking the cosmic speed limit, but by bending the rules of space-time itself? This is the tantalizing promise of the Alcubierre drive, a theoretical concept that could make faster-than-light travel a reality. Named after physicist Miguel Alcubierre, who first proposed the idea in 1994, this drive doesn't rely on moving a spacecraft through space at impossible speeds. Instead, it manipulates space-time itself, creating a warp bubble that carries the spacecraft along like a surfer riding a wave. It's a radical idea, one that challenges our understanding of physics and opens up the possibility of exploring the cosmos in ways that once seemed like pure science fiction. Here's how it works. Imagine space-time as a stretchy fabric, just like the trampoline we used earlier to describe gravity. The Alcubierre drive would contract space-time in front of the spacecraft, pulling the destination closer, while expanding space-time behind it, pushing the starting point farther away. The spacecraft itself would sit inside a flat, undisturbed region of space-time, protected from the extreme distortions happening around it. In this way, the ship wouldn't actually be moving through space at all. It would be carried along by the warp bubble, effectively sidestepping the speed of light limit. It's like folding a map to bring two distant cities closer together, then walking across the fold rather than traveling the full distance. But there's a catch. To create this warp bubble, the Alcubierre drive would require something called exotic matter, a theoretical substance with negative energy density. Unlike ordinary matter, which has positive energy and mass, exotic matter would have the bizarre property of repelling gravity rather than attracting it. This repulsion would be essential to generate the space-time distortions needed for the drive to work. The problem: exotic matter has never been observed in nature, and creating it in a lab is far beyond our current capabilities. Even if we could produce it, the energy requirements for an Alcubierre drive are staggering. Some estimates suggest it would take the equivalent of the entire mass energy of Jupiter just to power a modest-sized warp bubble. Another challenge is the sheer complexity of the physics involved. The Alcubierre drive isn't just about bending space-time, it's about controlling that bending with extreme precision. Any miscalculation could lead to catastrophic effects, like the spacecraft being torn apart by tidal forces or the warp bubble collapsing in on itself. And then there's the question of causality. If faster-than-light travel were possible, could it create paradoxes like arriving at a destination before you left? These are the kinds of mind-bending questions that physicists are still grappling with as they explore the feasibility of the Alcubierre drive. Despite these challenges, the concept has captured the imagination of scientists and science fiction fans alike. It's a bold idea that pushes the boundaries of what we know about space-time, forcing us to rethink the very nature of travel and exploration. The Alcubierre drive isn't just a tool for crossing vast cosmic distances, it's a window into the deeper mysteries of the universe, a reminder that the laws of physics are more flexible and surprising than we often assume. As we delve into the possibilities of the Alcubierre drive, we're not just exploring a new way to travel, we're challenging our understanding of the fabric of reality itself. It's a journey that takes us from the equations of general relativity to the cutting edge of theoretical physics, showing us that the cosmos is full of possibilities waiting to be uncovered. Whether or not the Alcubierre drive ever becomes a reality, it inspires us to dream bigger, to push the boundaries of what's possible, and to keep exploring the infinite mysteries of the universe. What if the universe, in all its vastness, is made up of tiny, indivisible building blocks, so small that they're beyond our ability to measure or even imagine? This is the realm of the Planck scale, the smallest meaningful units of space and time in physics. Named after physicist Max Planck, this scale represents the ultimate frontier of our understanding, where the familiar rules of space and time break down and the universe reveals its most fundamental structure. At this level, space isn't smooth and continuous like we experience in everyday life. It's thought to be pixelated, like a digital image made up of countless tiny dots. These pixels are so small that they're almost incomprehensible. The Planck length, for example, is about 1/1,000,000,000 of a trillionth of a trillionth of a millimeter. To put it in perspective, if you were to magnify an atom to the size of the observable universe, a Planck length would still be smaller than a single atom. But why does this tiny scale matter? The Planck scale isn't just a theoretical curiosity, it's where our current understanding of physics hits a wall. At these unimaginably small distances, the effects of quantum mechanics and gravity become equally significant, and the two frameworks, which have long resisted being unified, clash in dramatic ways. According to Einstein's general relativity, space-time is smooth and continuous, bending and warping under the influence of massive objects. But quantum mechanics tells us that everything, including space and time, is fundamentally discrete and granular. This contradiction suggests that our current theories are incomplete, and that a new framework, a quantum theory of gravity, is needed to bridge the gap. The Planck scale is where this new theory must emerge, offering a glimpse into the true nature of reality. Imagine zooming in on a digital photograph. At first, the image looks smooth and detailed, but as you get closer, you start to see the individual pixels that make up the picture. The Planck scale is like that. It's the point where the smoothness of space-time dissolves into a sea of tiny, discrete units. Some theories suggest that space-time itself might be made up of these Planck-sized quanta, creating a kind of cosmic pixelation. This idea has profound implications for our understanding of the universe. If space-time is pixelated at the Planck scale, it means that the fabric of reality isn't continuous but instead built from these ultra-tiny building blocks. It's a radical shift in how we think about the cosmos, suggesting that the universe might be more like a digital simulation than a smooth, flowing continuum. The Planck scale also raises fascinating questions about the nature of time. Just as space might be pixelated, time could also be broken into its smallest possible units, known as Planck time. This is the time it takes for light to travel 1 Planck length, and it's the shortest interval that can theoretically exist. At this scale, time might not flow smoothly like a river, but instead tick forward in discrete steps like the frames of a movie. This idea challenges our everyday experience of time as something continuous and unchanging, suggesting that even time itself might have a granular structure. Exploring the Planck scale isn't just about understanding the smallest units of space and time, it's about uncovering the fundamental nature of reality. It's here, at this unimaginably small scale, that the secrets of quantum gravity might be hiding, waiting to reveal how the universe truly works. As we push the boundaries of our knowledge, we're reminded that the cosmos is far stranger and more intricate than we ever imagined. The Planck scale isn't just a limit, it's a doorway inviting us to step into a deeper understanding of the universe and our place within it. And with each discovery, we move closer to unraveling the true fabric of existence. What if everything around us, every star, every galaxy, and even our own thoughts were part of an incredibly advanced simulation? This is the heart of the simulation hypothesis, a mind-bending idea that suggests our universe might not be real in the way we think. Instead, it could be an elaborate computer program crafted by an intelligent civilization far beyond our own. While it sounds like the plot of a sci-fi movie, this theory has gained serious traction among scientists, philosophers, and even tech leaders. It's a concept that doesn't just challenge our understanding of reality, it forces us to ask, what does it even mean to exist? At its core, the simulation hypothesis is rooted in the idea that the universe operates with a precision that feels almost mathematical. From the laws of physics to the behavior of subatomic particles, everything seems to follow a set of rules like lines of code in a program. Some argue that this mathematical structure is evidence that our reality could be computational in nature. After all, if you are creating a simulated universe, wouldn't you base it on a set of consistent, logical rules? This idea isn't just philosophical, it's tied to the way we understand space-time. In a simulated reality, space-time might not be a fundamental feature but rather a construct, a kind of rendering that the simulation uses to create the illusion of a continuous, flowing universe. But how could we possibly test this idea? One intriguing piece of evidence comes from the study of quantum mechanics. At the smallest scales, particles don't behave like solid objects, they exist in a haze of probabilities, only deciding their state when observed. Some theorists suggest that this behavior could be a sign of computational optimization. Imagine a video game that only renders the parts of the world the player is looking at. It saves processing power. In a similar way, the universe might only compute the details of reality when we're looking, as a way to conserve resources. It's a strange thought, but one that aligns with the simulation hypothesis. Another line of reasoning comes from the fine-tuning of the universe. The constants that govern physics, like the speed of light or the strength of gravity, are so precisely balanced that even the tiniest change would make life impossible. For some, this fine-tuning suggests that our universe was deliberately designed, whether by a higher power or a highly advanced civilization running a simulation. It's as if the universe was programmed with just the right parameters to allow stars, planets, and life to emerge. But does this mean we're living in a simulation, or is it simply a coincidence? The debate is far from settled. The simulation hypothesis also raises profound questions about the nature of existence. If we're living in a simulation, who created it? Are we part of an experiment, or are we simply characters in a cosmic story? And what happens if the simulation ends? These questions don't just challenge our understanding of the universe, they force us to confront the very meaning of life. It's a humbling idea, one that reminds us how much we still have to learn about the cosmos and our place within it. As we explore the simulation hypothesis, we're not just delving into a theory, we're stepping into a thought experiment that pushes the boundaries of science and philosophy. Whether or not our universe is a simulation, the idea invites us to think differently about reality, to question the assumptions we take for granted, and to marvel at the mysteries that still surround us. It's a journey that takes us from the tiniest particles to the vast expanse of space-time, showing us that the universe is far more complex and interconnected than we ever imagined. And as we continue to probe these deep questions, we're reminded that the cosmos is full of surprises, waiting for us to uncover them. If the universe is so vast and filled with countless stars and planets, why haven't we found any signs of intelligent life beyond Earth? This is the essence of the Fermi paradox, a question that has puzzled scientists and dreamers alike for decades. Named after physicist Enrico Fermi, who famously asked, "Where is everybody?" The paradox highlights a striking contradiction. Given the sheer size of the cosmos and the high probability that life could arise elsewhere, it seems almost inevitable that we should have encountered some form of extraterrestrial civilization by now. Yet, despite decades of searching, the skies remain silent. So, what's going on? Could space-time distortions hold the key to this cosmic mystery? One possibility is that advanced civilizations have already mastered the art of manipulating space-time, using technologies far beyond our current understanding. Imagine a species that has unlocked the secrets of wormholes, creating cosmic shortcuts to travel unimaginable distances in the blink of an eye. Such a civilization wouldn't need to send slow, cumbersome probes across the galaxy. They could simply fold space-time and vanish from one point, only to reappear light years away. From our perspective, they might seem to disappear entirely, leaving no trace of their existence. It's a tantalizing thought. What if the reason we haven't found aliens is because they're using technologies we can't even detect? But wormholes aren't the only space-time trick that might explain the Fermi paradox. Advanced civilizations could also be harnessing time dilation to their advantage. Picture a society that has built massive starships capable of traveling at a significant fraction of the speed of light. For them, a journey across the galaxy might take only a few years, while millennia pass for those left behind. To us, such a civilization might appear to vanish, their activities compressed into such a brief window of time that we'd never notice them. Alternatively, they might have retreated into regions of space where time flows differently, like near a black hole, effectively hiding in plain sight by existing in a different temporal frame. Then there's the possibility that extraterrestrial civilizations have simply moved beyond the need for physical exploration altogether. If a species becomes advanced enough, they might abandon the limitations of biological bodies and upload their consciousness into digital realms, existing as pure information. In this scenario, their presence wouldn't be marked by starships or cities, but by the faint hum of quantum computers processing the thoughts of countless beings. These digital civilizations could be all around us, operating in dimensions or frequencies we can't perceive, rendering them invisible to our current methods of detection. Of course, these are just a few imaginative scenarios, but they highlight how space-time distortions could play a role in resolving the Fermi paradox. The truth is, we're still in the early stages of understanding the universe, and our tools for detecting extraterrestrial life are limited. But what if one day humanity could harness these same technologies? Imagine a future where we've mastered wormholes, allowing us to explore distant stars without the constraints of light speed. Or a world where we've unlocked the secrets of time dilation, enabling us to journey across the galaxy in what feels like moments. Such advancements wouldn't just solve the Fermi paradox, they would transform our place in the cosmos, turning us from passive observers into active explorers of the universe's deepest mysteries. As we ponder the Fermi paradox, we're reminded of how much we still have to learn about the universe and our place within it. The silence of the cosmos might not be a sign that we're alone. It could be a challenge, an invitation to push the boundaries of our understanding and discover the technologies that will one day connect us to the stars. The journey to uncover these secrets is just beginning, and each step brings us closer to answering the question that has haunted us for generations: where is everybody? What if the universe wasn't just a random collection of stars and galaxies, but a carefully balanced system, perfectly tuned to allow life to exist? This is the essence of the Anthropic Principle, a fascinating idea that suggests the universe's properties are remarkably fine-tuned to support life as we know it. From the strength of gravity to the speed of light, the fundamental constants of nature seem to be set with astonishing precision. If any of these values were even slightly different, the universe as we know it wouldn't exist. Stars wouldn't form, atoms wouldn't hold together, and life itself would be impossible. So, why is the universe so perfectly suited for us? And what does this fine-tuning mean for our understanding of space-time and the nature of reality? To grasp the Anthropic Principle, let's start with a simple thought experiment. Imagine you're holding a remote control with 100 dials, each controlling a different aspect of the universe: gravity, electromagnetism, the nuclear forces, and so on. If you randomly twisted these dials, what are the odds that you'd land on a combination that allows for stars, planets, and life? The answer is almost zero. The universe we live in seems to have hit the cosmic jackpot, with all the dials set just right. This is what physicists call the fine-tuning problem, and it's one of the most profound mysteries in science. But how does this fine-tuning connect to space-time? One key piece of the puzzle lies in the universe's expansion rate. If space-time expanded too quickly after the Big Bang, matter would have spread out too thinly for galaxies to form. If it expanded too slowly, the universe would have collapsed back in on itself before stars could ignite. The expansion rate had to be just right, and it's tied directly to the balance of energy and matter in the cosmos. Similarly, the strength of gravity is finely calibrated. If gravity were stronger, stars would burn out too quickly. If it were weaker, they might never ignite at all. These delicate balances aren't just lucky coincidences, they're essential for the universe to function in a way that allows life to emerge. This raises a deeper question: why is the universe so hospitable to life? Some scientists argue that the Anthropic Principle provides an answer. In its simplest form, the principle suggests that we observe the universe's fine-tuning because, well, we're here to observe it. If the universe weren't fine-tuned, we wouldn't exist to ask the question. It's a bit like a puddle marveling at how perfectly it fits into the hole it occupies. The hole wasn't made for the puddle, but the puddle exists because of the hole's shape. In the same way, the universe's properties aren't tailored for us. We've evolved to fit the conditions it provides, but the Anthropic Principle doesn't stop there. It also opens the door to even more mind-bending ideas like the Multiverse Theory. If our universe is just one of countless others, each with its own set of physical constants, then it's not so surprising that we find ourselves in one where the conditions are just right for life. In this view, the fine-tuning isn't a mystery, it's a statistical inevitability. We just happen to live in the universe where the dice rolled in our favor. This idea doesn't just explain fine-tuning, it redefines our understanding of reality itself, suggesting that our universe is just one thread in an infinite cosmic tapestry. The implications of the Anthropic Principle go beyond just explaining the universe's properties. It could also guide the future of scientific discovery. If we accept that the universe is fine-tuned for life, it might shift how we approach questions about the nature of space-time, the origins of the cosmos, and even the search for extraterrestrial life. It reminds us that the universe isn't just a random collection of particles and forces, it's a dynamic, interconnected system, shaped by the delicate balance of its fundamental laws. And as we continue to explore these mysteries, we're not just uncovering facts about the universe, we're uncovering truths about our place within it. The Anthropic Principle isn't just a scientific idea, it's a lens through which we can view the cosmos with wonder and curiosity. It challenges us to think bigger, to ask deeper questions, and to marvel at the intricate design of the universe. Whether we're pondering the fine-tuning of gravity or the vastness of the multiverse, the Anthropic Principle reminds us that the universe is full of surprises waiting for us to uncover them. And as we continue to probe these mysteries, we're reminded that the journey to understand the cosmos is as much about discovering ourselves as it is about exploring the stars. What happens to information when it disappears into a black hole? It's a question that has haunted physicists for decades, and it lies at the heart of one of the most perplexing mysteries in modern science, the black hole information paradox. At first glance, the answer seems simple: anything that crosses a black hole's event horizon is lost forever, swallowed by an inescapable gravitational pull. But when we dig deeper, this seemingly straightforward idea collides with one of the most fundamental principles of quantum mechanics: information cannot be destroyed. It's a paradox that pits two of our most successful theories, general relativity and quantum mechanics, against each other, forcing us to rethink the very nature of space-time and the rules that govern the universe. Let's break it down. According to quantum mechanics, information is sacred. Every particle, every interaction leaves a trace, a kind of cosmic fingerprint that tells the story of its existence. Even if you burn a book, the information it contained isn't truly gone. It's just transformed into heat, light, and ash. But black holes seem to defy this rule. When matter falls into a black hole, it's crushed into an infinitely dense point called a singularity, where the laws of physics as we know them break down. According to classical physics, that information is lost forever, erased from the universe. This creates a glaring contradiction. If quantum mechanics is correct, information must be preserved, but if general relativity holds true, it's gone for good. So, which one is right? One proposed solution comes from the holographic principle, an idea we touched on earlier. This theory suggests that all the information about the matter that falls into a black hole isn't lost, it's encoded on the black hole's event horizon, the boundary beyond which nothing can escape. Imagine the event horizon as a kind of cosmic hard drive, storing every detail about the objects that cross it. Over time, this information is slowly released back into the universe as Hawking radiation, the faint glow of particles that black holes emit. In this scenario, the information isn't destroyed, it's just scrambled, like a jigsaw puzzle waiting to be reassembled. But while this idea elegantly resolves the paradox, it raises new questions. How exactly does the information get encoded and decoded? And what happens to it inside the black hole? Another radical solution is the Firewall hypothesis, which suggests that the event horizon isn't the calm, uneventful boundary we once thought. Instead, it could be a blazing wall of energy, incinerating anything that comes near it. In this scenario, the information is destroyed not by the singularity, but by the firewall itself. It's a dramatic idea, but one that challenges Einstein's predictions and raises even more questions. If firewalls exist, what does that mean for the nature of space-time? And how does this fit with our understanding of quantum mechanics? The black hole information paradox isn't just a theoretical puzzle, it's a window into the deeper mysteries of the universe. Resolving it could revolutionize our understanding of space-time, quantum mechanics, and even the nature of reality itself. It's a reminder that the cosmos is far stranger and more complex than we often assume, filled with phenomena that defy our everyday experience. As we continue to grapple with these questions, we're not just uncovering new facts about black holes, we're rewriting the rulebook of physics itself. The journey to solve the information paradox is far from over, and each new discovery brings us closer to understanding the true nature of the universe we call home. What if the universe isn't just expanding, but doing so at an ever-increasing speed, as if pushed by an invisible hand? This is the mystery of dark energy, one of the most perplexing and powerful forces in the cosmos. Unlike anything we've encountered before, dark energy isn't a substance or a particle. It's more like a property of space itself, a kind of cosmic tension that permeates the universe, driving galaxies apart at an accelerating rate. It's as if the fabric of space-time is stretching, not because of something acting on it, but because of an inherent energy woven into its very structure. But what exactly is dark energy, and how does it shape the universe we see today? To understand dark energy, let's start with the evidence that brought it to light. In the late 1990s, astronomers studying distant supernovae made a startling discovery. These exploding stars, which act as cosmic mile markers, were fainter than expected, suggesting they were farther away than they should have been. The only explanation was that the universe wasn't just expanding, it was accelerating. This discovery turned cosmology on its head. Until then, most scientists believed that the expansion of the universe, set in motion by the Big Bang, would gradually slow down due to gravity's pull. But the data told a different story. Something was counteracting gravity, pushing the universe to expand faster and faster. That something is what we now call dark energy. But how does dark energy work? Imagine space-time as a rubber sheet stretched tight. Now, picture an invisible spring beneath it, pulling the sheet outward in all directions. That's dark energy, a force that doesn't just resist gravity, but actively works against it, stretching the fabric of the cosmos. Unlike gravity, which pulls objects together, dark energy pushes them apart, and its effects become more pronounced as the universe grows larger. In the early universe, when matter was densely packed, gravity dominated. But as space expanded and matter spread out, dark energy began to take over, driving the acceleration we observe today. The implications of dark energy are profound. It makes up roughly 68% of the universe's total energy content, dwarfing both ordinary matter and dark matter. Yet, despite its dominance, we know almost nothing about it. Is it a constant force, or does it change over time? Could it be connected to the quantum fluctuations that fill the vacuum of space? Or is it something entirely new, a fundamental aspect of the universe we've yet to comprehend? These questions aren't just academic. They could hold the key to understanding the ultimate fate of the cosmos. One of the most intriguing possibilities is that dark energy could be tied to the very nature of space-time itself. Some theories suggest it might be related to the cosmological constant, a term Einstein introduced into his equations of general relativity to describe a static universe. When the universe was found to be expanding, Einstein famously called the cosmological constant his greatest blunder. But now, with dark energy in the picture, it seems he might have been onto something after all. If dark energy is the cosmological constant, it would mean that empty space isn't truly empty. It contains a latent energy that drives the universe's expansion. Understanding dark energy could also shed light on the deeper mysteries of space-time. For instance, if dark energy changes over time, it might reveal hidden connections between the large-scale structure of the universe and the quantum realm. It could even help us unravel the nature of gravity itself, bridging the gap between general relativity and quantum mechanics. The study of dark energy isn't just about explaining the universe's expansion, it's about unlocking the secrets of reality on the grandest scales. As we continue to probe the mysteries of dark energy, we're reminded that the universe is far stranger and more dynamic than we ever imagined. It's a force that shapes the cosmos in ways we're only beginning to understand, and its discovery has opened up new frontiers in our quest to understand space, time, and the very fabric of existence. The story of dark energy is far from over, and each new discovery brings us closer to unraveling the true nature of the universe we call home. What if the universe is held together by an invisible force, one we can't see, touch, or even detect directly? This is the enigma of dark matter, a mysterious substance that makes up about 27% of the universe's total mass and energy. Unlike dark energy, which pushes the universe apart, dark matter acts as a kind of cosmic glue, holding galaxies and galaxy clusters together through its gravitational pull. Without it, the universe as we know it wouldn't exist. Stars would fly apart, galaxies would unravel, and the cosmos would be a very different place. But what exactly is dark matter, and how does it shape the fabric of space-time? The story of dark matter begins with the motion of galaxies. In the 1930s, astronomer Fritz Zwicky noticed something strange about the Coma cluster, a group of galaxies millions of light-years away. The galaxies were moving so fast that, based on the visible matter alone, the cluster should have flown apart. Yet it held together. Zwicky proposed that there must be some unseen mass, what he called dark matter, providing the extra gravitational pull needed to keep the cluster intact. Decades later, Vera Rubin and her colleagues found similar evidence in individual galaxies. By studying the rotation curves of spiral galaxies, Rubin discovered that stars on the outer edges were orbiting just as fast as those near the center. According to the laws of gravity, this shouldn't happen unless there was a vast amount of invisible matter surrounding the galaxies, exerting a gravitational influence. So, what is this invisible matter? The truth is, we don't know for sure. Dark matter doesn't emit, absorb, or reflect light, making it completely invisible to our telescopes. Yet, its presence is felt everywhere. Imagine a cosmic scaffold, an invisible framework that holds galaxies and galaxy clusters together. This scaffold doesn't just support the visible universe, it shapes the very fabric of space-time. Just as massive objects like stars and planets warp space-time, dark matter's gravitational effects create ripples and distortions that guide the movement of galaxies and influence the large-scale structure of the cosmos. It's as if the universe is a vast, intricate tapestry with dark matter woven into its very threads. But how do we know dark matter is real if we can't see it? The answer lies in its effects. One of the most compelling pieces of evidence comes from gravitational lensing, a phenomenon where the gravity of a massive object like a galaxy cluster bends the light from objects behind it. By studying these distorted images, scientists can map the distribution of mass in the cluster, including the invisible dark matter. These maps reveal that dark matter forms vast, web-like structures that stretch across the universe, connecting galaxies and galaxy clusters in a cosmic network. It's a hidden architecture, invisible to the eye but essential to the universe's structure. Dark matter's influence extends beyond just shaping galaxies. It also plays a crucial role in the formation of the universe itself. In the early cosmos, dark matter acted as a gravitational seed, pulling ordinary matter together to form the first stars and galaxies. Without it, the universe might have remained a diffuse sea of gas, never coalescing into the structures we see today. This interplay between dark matter and ordinary matter is a key part of the cosmic story, one that continues to shape the evolution of the universe. Yet, despite its importance, dark matter remains one of the greatest mysteries in science. What is it made of? Is it a particle or something entirely different? And how does it interact with other space-time phenomena like black holes or gravitational waves? These questions are at the forefront of modern physics, driving experiments deep underground in particle accelerators and even in space. As we search for answers, we're not just uncovering the secrets of dark matter, we're exploring the hidden forces that shape the cosmos. The journey to understand dark matter is far from over, and each discovery brings us closer to unraveling the true nature of the universe we call home. What if space-time, the very fabric of the universe, isn't the foundation of reality, but something that emerges from a deeper, more fundamental layer? This is the radical idea behind emergent space-time, a theory that challenges one of our most basic assumptions about the cosmos. For centuries, we've thought of space and time as the stage on which everything else plays out, a fixed, unchanging backdrop against which the drama of the universe unfolds. But what if space-time isn't fundamental at all? What if it's more like a tapestry woven from countless tiny threads that we can't yet see? This isn't just a philosophical musing, it's a serious scientific idea, one that arises from the quest to unify quantum mechanics and general relativity. To understand emergent space-time, let's start with the holographic principle, a concept we touched on earlier. This principle suggests that all the information about a three-dimensional volume of space can be encoded on its two-dimensional boundary like a hologram. If this is true, then the three-dimensional universe we experience might not be fundamental. It could emerge from a more basic two-dimensional reality. It's as if the universe is a projection, a kind of cosmic illusion created by the interactions of quantum information on a deeper level. This idea doesn't just change how we think about space, it redefines our understanding of reality itself. But how does this connect to quantum gravity? Quantum gravity is the theoretical framework that seeks to unify quantum mechanics, which governs the smallest particles, with general relativity, which describes the largest structures in the universe. At the heart of this quest is the idea that space-time might not be smooth and continuous, as Einstein described, but instead made up of discrete, indivisible units like pixels on a screen. These units, often referred to as space-time quanta, could be the fundamental building blocks from which space-time emerges. Imagine a digital photograph. When you zoom in, you see individual pixels, but from a distance, the image appears smooth and continuous. In the same way, space-time might appear smooth on large scales, but be fundamentally pixelated at the smallest levels. This idea of emergent space-time has profound implications for our understanding of reality. If space-time isn't fundamental, then the way we think about the universe, its structure, its evolution, even its very existence might need to be completely reimagined. For example, the Big Bang might not be the beginning of space-time, but rather a transition from one state to another, like a phase change in a material. Similarly, black holes might not be singularities where space-time breaks down, but regions where the underlying quantum structure of space-time becomes visible. These are just a few of the possibilities that emerge when we consider space-time as something that arises from a deeper reality. One of the most striking implications of emergent space-time is that it could solve some of the deepest puzzles in physics. For instance, it might explain the nature of dark energy or the behavior of particles at the quantum level. It could also provide a new way to understand the universe's expansion, suggesting that space-time itself evolves as the cosmos grows. This idea doesn't just reshape our understanding of the universe, it opens up new avenues for exploration, inviting us to think about reality in ways we've never considered before. As we explore the concept of emergent space-time, we're reminded that the universe is far stranger and more complex than we often assume. It's a reminder that the questions we ask and the answers we seek are only the beginning of a much larger story. The journey to understand space-time isn't just about uncovering new facts, it's about redefining what we think is possible. And with each new discovery, we're not just learning about the universe, we're discovering a deeper, more interconnected reality, one that challenges us to think bigger and dream larger than ever before. What if the very act of observing the universe changes it? It's a question that has puzzled scientists and philosophers for decades, and it lies at the heart of one of the most intriguing ideas in modern physics, the role of consciousness in shaping reality. At first glance, it sounds like something out of science fiction, an idea that blurs the line between the observer and the observed. But when we dig deeper, we find that this concept isn't just philosophical, it's rooted in the strange and counterintuitive world of quantum mechanics. The story begins with the observer effect, a phenomenon where the act of measuring a quantum system seems to influence its behavior. Take, for example, the famous double-slit experiment. When particles like electrons or photons are sent through two slits, they create an interference pattern on a screen, behaving like waves. But when scientists try to observe which slit the particles pass through, the interference pattern disappears and the particles behave like discrete particles instead. It's as if the very act of observation collapses the wave-like behavior into a single, definite state. This has led some to suggest that consciousness, the act of observing, might play a fundamental role in determining the nature of reality. But how far does this idea go? Could consciousness actually shape space-time itself? Some theorists argue that the observer effect isn't just about measurement, it's about the presence of a conscious mind. In this view, reality isn't a fixed, objective entity, but something that emerges through interaction with consciousness. It's a radical idea, one that challenges our traditional notions of objectivity and the separation between the observer and the observed. Imagine the universe as a kind of cosmic canvas, with consciousness acting as the brush that paints reality into existence. It's a provocative thought, but one that raises profound questions about the nature of existence. This idea isn't just limited to quantum mechanics, it also connects to broader philosophical questions about the nature of reality. If consciousness plays a role in shaping the universe, what does that mean for our understanding of space and time? Could the flow of time, the structure of space, or even the laws of physics be influenced by the presence of conscious observers? Some theories suggest that consciousness might be a fundamental feature of the universe, as essential as space-time or energy. In this view, the universe isn't just a collection of particles and forces, it's a dynamic participatory system, shaped by the minds that inhabit it. Of course, this idea is highly controversial. Many scientists argue that the observer effect can be explained without invoking consciousness, pointing to the role of measurement devices and the environment in collapsing quantum states. They caution against conflating the act of observation with the presence of a conscious mind, emphasizing that the observer effect is a physical process, not a mental one. Yet, even within this framework, the question remains, what is the true nature of reality, and how much of it is shaped by our interaction with it? The debate over consciousness and reality doesn't just challenge our understanding of physics, it forces us to rethink the very nature of existence. If consciousness plays a role in shaping the universe, it blurs the line between the subjective and the objective, the mental and the material. It invites us to consider that the universe might not be a static, predetermined system, but a dynamic, evolving reality, shaped in part by the minds that observe it. Whether or not this idea holds up to scientific scrutiny, it opens up a fascinating dialogue between science and philosophy, one that pushes the boundaries of what we know and what we dare to imagine. As we explore the role of consciousness in shaping reality, we're reminded that the universe is far more mysterious and interconnected than we often assume. It's a journey that takes us from the smallest particles to the vast expanse of space-time, showing us that the cosmos is not just something we observe, it's something we participate in. And as we continue to probe these deep questions, we're not just uncovering new facts about the universe, we're discovering a deeper, more profound relationship between the observer and the observed, the mind and the cosmos. The story of consciousness and reality is far from over, and each new discovery brings us closer to understanding the true nature of the universe we call home. What if the next decade holds the key to unlocking the deepest secrets of space-time? The future of space-time research is brimming with possibilities, fueled by cutting-edge technologies and bold new ideas. From advanced telescopes that peer deeper into the cosmos than ever before to particle accelerators that recreate the conditions of the early universe, scientists are on the brink of discoveries that could reshape our understanding of reality. Imagine a world where we can finally test theories about wormholes, dark energy, and even the nature of time itself. The tools we're building today could soon make these once fanciful ideas a reality. One of the most exciting frontiers is the development of next-generation telescopes. Instruments like the James Webb Space Telescope and the upcoming Extremely Large Telescope aren't just more powerful, they're designed to capture details that were once invisible to us. These telescopes will allow us to study the earliest moments of the universe, observe the formation of galaxies, and even detect the faint ripples of gravitational waves from colliding black holes. With these tools, we might uncover clues about the nature of dark matter or find evidence of multiverses. It's like having a time machine that lets us peer billions of years into the past, revealing the origins of space-time itself. But telescopes aren't the only tools in our arsenal. Particle accelerators like the Large Hadron Collider are pushing the boundaries of what we know about the fundamental forces of nature. By smashing particles together at nearly the speed of light, these machines recreate the intense conditions of the early universe, allowing us to study phenomena that can't be observed anywhere else. Future accelerators like the proposed Future Circular Collider could be even more powerful, potentially revealing new particles or forces that could explain the mysteries of dark energy or quantum gravity. These experiments aren't just about discovering new particles, they're about probing the very fabric of space-time, exploring how it behaves under extreme conditions and uncovering the rules that govern its structure. Another promising area of research is the study of quantum entanglement and its connection to space-time. Recent experiments have shown that entangled particles can influence each other instantaneously, even across vast distances. This phenomenon, once dismissed as spooky action at a distance, might hold the key to understanding how space-time is woven together at the most fundamental level. Scientists are now developing quantum computers and sensors that could help us explore this connection, potentially leading to breakthroughs in our understanding of gravity, the Big Bang, and even the nature of reality itself. As we push the boundaries of technology, we're also developing new ways to test revolutionary theories. For instance, the search for gravitational waves, ripples in space-time caused by cataclysmic events like black hole mergers, has opened up an entirely new way to observe the universe. Future detectors like the Laser Interferometer Space Antenna, or LISA, will be able to detect waves from even more distant and massive events, providing insights into the behavior of space-time on cosmic scales. These observations could help us test theories about the early universe, the nature of black holes, and even the possibility of extra dimensions. The future of space-time research isn't just about building bigger machines, it's about asking bigger questions. What if we could manipulate space-time to create a warp drive, enabling faster-than-light travel? What if we discover that space-time isn't fundamental but emerges from a deeper quantum reality? These aren't just thought experiments, they're real possibilities that could transform our understanding of the universe. As we continue to explore these questions, we're not just uncovering new facts, we're redefining what it means to exist within the cosmos. The coming decades promise to be a golden age of discovery where the boundaries of science and imagination blur. With every new experiment, every new observation, we're inching closer to answers that could change everything we know about space, time, and the nature of reality. It's a future filled with wonder, challenge, and endless possibility, one that invites us all to be part of the journey. As we stand on the edge of these new frontiers, we're reminded that the universe is far more vast, complex, and beautiful than we ever imagined. And with each step forward, we're not just exploring the cosmos, we're uncovering the story of existence itself. Imagine a world where we could bend the fabric of space-time to our will, where time travel isn't just a plot device in sci-fi movies, but a real, tangible possibility. What would that mean for humanity? Beyond the scientific breakthroughs and the thrill of exploration, the ability to manipulate space-time raises profound ethical questions that challenge our understanding of responsibility, morality, and the very nature of existence. If we could alter the past, visit the future, or create entirely new universes, how would we decide what's right and wrong? These aren't just hypothetical musings, they're dilemmas we might one day face as we push the boundaries of physics and technology. Let's start with time travel, perhaps the most iconic form of space-time manipulation. The ability to revisit the past or leap into the future isn't just a scientific challenge, it's an ethical minefield. Consider the classic grandfather paradox. If you traveled back in time and accidentally prevented your own birth, what would happen to your existence? Beyond the logical conundrums, there's the question of interference. If you could change a single moment in history, would it be ethical to prevent a tragedy, knowing that altering the past could have unintended consequences for the present and future? The ripple effects of even the smallest change could cascade into a completely different reality, raising questions about accountability and the nature of free will. Wormholes, too, present their own set of ethical challenges. If we could create stable wormholes enabling instant travel across vast distances, who would control access to this technology? Would it become a tool for exploration and connection, or a weapon for domination? The potential for misuse is staggering. Imagine a scenario where a single nation or corporation monopolizes wormhole technology, using it to exploit resources on distant planets or even manipulate events on a cosmic scale. The ethical implications extend beyond Earth, forcing us to consider how we might interact with other civilizations or ecosystems we encounter. Would we have the right to impose our will on other worlds, or would we be bound by a universal code of ethics? Then there's the mind-bending possibility of creating artificial universes. If we could engineer a new reality, complete with its own laws of physics and timelines, what responsibilities would we have to the beings who might emerge within it? Would we be creators, stewards, or something else entirely? This idea isn't just speculative, it ties into ongoing debates about artificial intelligence and the ethics of creating sentient life. If we can design universes, do we have a moral obligation to ensure they're free from suffering? Or would such a universe be a canvas for experimentation with all the ethical quandaries that implies? These scenarios aren't just thought experiments, they're windows into the ethical challenges we might face as we advance our understanding of space-time. They force us to confront questions about power, responsibility, and the limits of human ambition. How do we balance the pursuit of knowledge with the potential consequences of our discoveries? And who gets to decide the rules in a universe where the boundaries of possibility are constantly shifting? Navigating these challenges will require more than just scientific ingenuity. It will demand a global conversation about ethics, governance, and the values we want to uphold as a species. We'll need frameworks for decision-making that prioritize transparency, inclusivity, and accountability. International cooperation will be essential, as will the involvement of ethicists, philosophers, and the public. After all, the ability to manipulate space-time isn't just a scientific achievement, it's a shared responsibility that could redefine what it means to be human. As we stand on the brink of these possibilities, we're reminded that the future of space-time research isn't just about unlocking the secrets of the cosmos, it's about shaping the kind of universe we want to live in. The choices we make today as we explore these uncharted territories will echo across time and space, leaving a legacy that extends far beyond our own existence. The journey ahead is as much about ethics as it is about science, and it invites us all to be part of the conversation. What kind of future will we create? The answer lies not just in our discoveries, but in the values we choose to guide them. What if the universe isn't just a collection of stars and galaxies, but a profound puzzle that forces us to question the very nature of reality? Revolutionary theories about space-time distortions don't just challenge our scientific understanding, they shake the foundations of philosophy itself. From the fluid nature of time to the mind-bending possibilities of wormholes and parallel universes, these ideas force us to confront age-old questions about determinism, free will, and what it means to exist. How can we reconcile the idea of a universe governed by strict physical laws with the intuitive sense that we have control over our own lives? And if space-time is more malleable than we once thought, what does that mean for the nature of existence? These are the kinds of questions that bridge the gap between science and philosophy, inviting us to rethink not just the cosmos but our place within it. Take determinism, for example, the idea that every event is the inevitable result of prior causes. In a universe where space-time is fixed and unyielding, it's easy to see how this philosophy might hold sway. But what happens when we introduce the idea of time dilation, where time can stretch and warp depending on speed or gravity? Suddenly, the rigid flow of cause and effect becomes far more fluid. As physicist Brian Greene once put it, time is not absolute, it's a flexible, dynamic thing. This flexibility challenges the deterministic view, suggesting that time itself might not be as straightforward as we once thought. It raises the possibility that the future isn't set in stone, but shaped by the intricate interplay of space, time, and the choices we make along the way. And then there's free will, a concept that has puzzled philosophers for centuries. If space-time can be bent, twisted, or even traversed, does that mean our choices are truly free, or are they still bound by the fabric of the universe? Some argue that the quantum nature of reality, with its inherent uncertainties, leaves room for genuine freedom. Others, like philosopher Daniel Dennett, suggest that free will might be a kind of illusion, a useful construct that helps us navigate a complex world. But what if the ability to manipulate space-time changes the equation entirely? If we could one day create wormholes or travel through time, would that give us the power to rewrite our own destinies, or would it reveal that free will was never truly ours to begin with? Perhaps the most profound philosophical question raised by space-time theories is the nature of existence itself. If the universe is a vast, interconnected web of space-time, what does that say about our place within it? Are we merely passive observers, or do we play an active role in shaping reality? The holographic principle, for instance, suggests that the information about our three-dimensional world might be encoded on a two-dimensional surface. If true, this idea blurs the line between the physical and the abstract, suggesting that reality itself might be a kind of projection. As philosopher Nick Bostrom has speculated, if the universe is a simulation, then our existence might be more like a thought experiment than a physical reality. This idea doesn't just challenge our understanding of space-time, it forces us to ask what it even means to be real. These philosophical debates aren't just academic, they have real-world implications for how we see ourselves and the universe. If space-time is more fluid and interconnected than we once thought, it could reshape our sense of identity, morality, and purpose. It invites us to think of ourselves not as isolated individuals, but as part of a vast, dynamic cosmos where every action ripples across space and time. This perspective doesn't just enrich our understanding of the universe, it deepens our appreciation for the profound mysteries that still surround us. As we explore the philosophical impact of space-time theories, we're reminded that science and philosophy are two sides of the same coin. Together, they help us navigate the complexities of existence, offering insights that go beyond the equations and experiments. Whether we're pondering the nature of free will or the possibility of alternate realities, these ideas challenge us to think bigger, to dream deeper, and to embrace the wonder of a universe that is far more mysterious and interconnected than we ever imagined. The journey to understand space-time isn't just about unlocking the secrets of the cosmos, it's about discovering what it means to be human in a universe that is constantly rewriting the rules. What if the mysteries of space-time aren't just the domain of scientists, but a source of endless inspiration for storytellers, artists, and dreamers? Throughout history, humanity's fascination with the cosmos has shaped our culture, giving rise to some of the most iconic works of art, literature, and film. From the mind-bending journeys of Interstellar to the time-hopping adventures of Doctor Who, space-time mysteries have captured our imaginations, reflecting our deepest questions about existence and our place in the universe. These stories aren't just entertainment, they're a mirror reflecting our collective curiosity and the limitless possibilities of the unknown. Take Christopher Nolan's Interstellar, for example. This visually stunning film doesn't just explore the science of black holes and time dilation. It weaves these concepts into a deeply human story about love, sacrifice, and survival. The film's depiction of a black hole, known as Gargantua, was so scientifically accurate that it led to new insights in astrophysics. But beyond the science, Interstellar taps into something universal: the idea that time, no matter how fluid or distorted, is inseparable from our emotions and relationships. It's a reminder that space-time isn't just a cold, mathematical concept, it's a framework that shapes our lives in profound and often poetic ways. Then there's Doctor Who, the long-running British series that has become a cultural phenomenon. With its iconic time machine, the TARDIS, the show has spent decades exploring the wonders and dangers of time travel. From historical events to distant futures, Doctor Who uses the fluidity of time as a narrative playground, blending science fiction with themes of morality, identity, and the resilience of the human spirit. The Doctor's adventures remind us that time isn't just a straight line, it's a tapestry, rich with possibilities and ripe for exploration. The show's enduring popularity speaks to our timeless fascination with the mysteries of space-time and the stories they inspire. But it's not just film and television that have been shaped by these ideas. Literature, too, has embraced the enigmas of space-time, from H.G. Wells' The Time Machine to contemporary works like Ted Chiang's Story of Your Life, which inspired the film Arrival. These stories challenge us to think beyond the constraints of linear time, exploring what it means to experience life in a universe where past, present, and future might not be as fixed as they seem. They invite us to imagine alternate realities, parallel worlds, and the profound connections that bind us across time and space. Even visual art has been touched by these mysteries. The surrealist works of Salvador Dali, with their melting clocks and distorted landscapes, evoke the fluidity of time, while contemporary artists like Olafur Eliasson use light and space to create immersive experiences that challenge our perceptions of reality. These creations aren't just about aesthetics, they're a way of grappling with the same questions that scientists ask. What is time? What is space? And how do they shape our understanding of existence? The cultural influence of space-time mysteries isn't just a reflection of our curiosity, it's a testament to the power of creativity. These stories and artworks don't just entertain or inspire, They push us to think differently, to question the boundaries of what we know, and to imagine new possibilities. They remind us that the universe isn't just a collection of facts and figures, it's a source of wonder, a canvas for our imaginations, and a constant invitation to explore the unknown. As we look to the future, these cultural touchstones continue to inspire new generations of creators. Whether it's a filmmaker imagining the next great space odyssey, a writer crafting a tale of time-traveling heroes, or an artist capturing the essence of a black hole on canvas, the mysteries of space-time will always be a wellspring of creativity. They remind us that the cosmos isn't just something to be studied, it's something to be experienced, interpreted, and celebrated. And in that celebration, we find not just answers, but a deeper connection to the universe and to each other. What if the boundaries between science and spirituality aren't as rigid as we once thought? For centuries, these two realms have often been seen as separate science dealing with the measurable, the tangible, while spirituality explores the intangible, the mystical. But as our understanding of space-time deepens, we're beginning to see fascinating overlaps between these worlds. From the unity of the cosmos to the nature of consciousness, revolutionary theories about space-time are sparking conversations that bridge the gap between the empirical and the existential. It's a meeting point where the cold logic of physics meets the warm mystery of the human spirit, inviting us to explore reality in ways that are both profound and deeply personal. Take, for example, the concept of unity, a central theme in both quantum physics and many spiritual traditions. In quantum mechanics, particles can become entangled, their fates intertwined across vast distances, as if they're part of a single, interconnected system. This idea resonates with spiritual teachings that emphasize the oneness of all existence. As the Dalai Lama once said, the universe is a single, unified entity. To see it as fragmented is an illusion. This parallel isn't just poetic, it's a reminder that the universe at its core might be far more interconnected than we've ever imagined. Whether we're talking about entangled particles or the threads of consciousness that bind us all, the idea of unity challenges us to see the cosmos not as a collection of separate parts, but as a seamless whole. Then there's the nature of consciousness itself, a topic that has fascinated both scientists and spiritual seekers for centuries. While science often treats consciousness as an emergent property of the brain, some theories suggest it might be something more fundamental, woven into the fabric of space-time. Physicist Sir Roger Penrose, for instance, has proposed that consciousness could be tied to quantum processes occurring in the brain's microtubules, hinting at a deeper connection between mind and matter. This idea echoes ancient spiritual traditions that view consciousness as the foundation of reality, a force that permeates everything from the smallest atom to the vast expanse of the universe. As spiritual teacher Eckhart Tolle puts it, consciousness is the intelligence that flows through all of creation. Could it be that consciousness isn't just a byproduct of the brain, but a fundamental aspect of the cosmos itself? These intersections between science and spirituality don't just deepen our understanding of the universe, they challenge us to rethink our place within it. If space-time is as fluid and interconnected as modern physics suggests, what does that mean for our sense of self? Are we truly separate individuals, or are we expressions of a larger, unified reality? These questions push us to explore not just the outer reaches of the cosmos, but the inner landscapes of our own minds and souls. They invite us to see science and spirituality not as opposing forces, but as complementary ways of understanding the same profound truth, that the universe is far more mysterious and interconnected than we ever imagined. The dialogue between science and spirituality isn't just theoretical, it has practical implications for how we live our lives. If we accept that the universe is a unified, conscious entity, it changes how we relate to each other and the world around us. It invites us to approach life with a sense of wonder and reverence, to see ourselves not as isolated beings, but as part of a vast, dynamic whole. As physicist Carl Sagan once said, "We are a way for the cosmos to know itself." This idea isn't just beautiful, it's empowering, reminding us that we're not just observers of the universe, but active participants in its unfolding story. As we explore these connections, we're reminded that the journey to understand space-time isn't just about unraveling the mysteries of the cosmos. It's about discovering what it means to be human in a universe that is both infinitely vast and intimately connected. The intersection of science and spirituality offers us a new way to see reality, one that embraces both the measurable and the mystical, the logical and the luminous. It's a perspective that invites us to explore the universe not just with our minds, but with our hearts, and to find meaning not just in the stars, but in the very fabric of our existence. So, after all this wormholes, time dilation, holographic universes, and the mysteries of dark energy, we're left with one ultimate question: what is reality? Not just the reality we see and touch, but the deeper, more fundamental reality that lies beneath it all. If space-time can bend, twist, and even emerge from a deeper quantum fabric, what does that say about the nature of existence itself? Are we living in a fixed, objective universe, or is reality something far more fluid, something that shifts and changes depending on how we observe it? These aren't just abstract questions, they're at the heart of everything we've explored, and they challenge us to rethink not just the cosmos, but our place within it. Think about it. If the universe is a hologram with all its information encoded on a two-dimensional surface, does that mean the three-dimensional world we experience is just an illusion? Or if time isn't a straight line but a branching tree of possibilities, does that mean every decision we make creates a new reality? These ideas don't just stretch the boundaries of science, they stretch the boundaries of what it means to exist. They force us to ask, is reality something we discover, or is it something we create? And if it's the latter, what does that say about the nature of consciousness, free will, and the very fabric of existence? Let's take it a step further. If space-time is as malleable as these theories suggest, could reality itself be a kind of cosmic construction, shaped not just by the laws of physics, but by the way we perceive and interact with it? This idea isn't new. It's been explored in philosophy and spirituality for centuries, but modern physics is giving it new weight. Think about quantum mechanics, where the act of observation seems to influence the behavior of particles. It's as if reality isn't a fixed thing, but a dynamic process, something that unfolds in response to our presence. And if that's true, what does it mean for our understanding of the universe? Are we passive observers, or are we active participants, co-creators of the reality we inhabit? These questions don't just challenge our understanding of the cosmos, they challenge our understanding of ourselves. If reality is more fluid and interconnected than we once thought, it changes how we see our place in the universe. It invites us to think of ourselves not as isolated individuals, but as part of a vast dynamic web where every action ripples across space and time. This perspective doesn't just deepen our appreciation for the mysteries of the universe, it deepens our connection to each other and the world around us. As we reflect on these ideas, we're reminded that the journey to understand space-time isn't just about unraveling the secrets of the cosmos. It's about discovering what it means to be human in a universe that is constantly rewriting the rules. It's a journey that takes us from the smallest particles to the vast expanse of the universe, showing us that the cosmos is far more mysterious and interconnected than we ever imagined. And as we continue to probe these deep questions, we're not just uncovering new facts, we're uncovering a deeper, more profound reality, one that challenges us to think bigger and dream larger than ever before. So, as we come to the end of this exploration, let's take a moment to reflect on what we've learned. The universe is not just a collection of stars and galaxies, it's a living, breathing entity, filled with mysteries that inspire us to ask, to wonder, and to explore. And while we may not have all the answers, the journey itself is a reminder of the boundless possibilities that lie ahead. The ultimate question, what is reality, isn't just a puzzle to solve. It's an invitation to keep exploring, to keep questioning, and to keep marveling at the infinite wonders of the cosmos. As we reach the end of this cosmic journey, it's worth taking a moment to reflect on the incredible ideas we've explored. From the mind-bending possibilities of wormholes and time dilation to the enigmatic nature of black holes and the holographic universe, each theory pushes the boundaries of what we thought was possible. These revolutionary concepts don't just challenge our understanding of space-time, they invite us to reimagine the very fabric of reality itself. They remind us that the universe is far stranger, more interconnected, and more mysterious than we ever dared to dream. Think about the sheer audacity of these ideas. Wormholes, those cosmic shortcuts, suggest that space-time isn't just a backdrop but a dynamic, malleable medium that can be folded and shaped. Time dilation, a consequence of Einstein's relativity, reveals that time itself is fluid, stretching and contracting depending on speed and gravity. Black holes, those enigmatic regions of infinite density, challenge our notions of cause and effect, while the holographic principle hints that the three-dimensional universe we experience might be a projection of a deeper, two-dimensional reality. And then there's the multiverse, the idea that our universe might be just one of countless others, each with its own unique set of physical laws. These theories aren't just science fiction, they're the cutting edge of modern physics, offering glimpses into a cosmos that defies imagination. But what does all this mean for us beyond the awe-inspiring science? These ideas remind us of the boundless potential of human curiosity. They show us that the universe is a place of infinite possibility, where even the most outlandish ideas can lead to profound discoveries. They challenge us to think bigger, to ask deeper questions, and to embrace the unknown with a sense of wonder and humility. As Carl Sagan once said, somewhere, something incredible is waiting to be known. And in the realm of space-time distortions, that something might be closer than we think. The journey doesn't end here. Each question we answer opens the door to a dozen more, and every discovery brings us closer to understanding the true nature of the cosmos. So let's keep exploring, keep questioning, and keep marveling at the mysteries that surround us. What do you think about these revolutionary theories? Do they spark your imagination, or do they leave you with even more questions? Share your thoughts in the comments. We'd love to hear your perspective. As we close this chapter, let's leave you with a thought to ponder. The universe isn't just something we observe, it's something we're a part of. Every star, every galaxy, every ripple in space-time is a piece of a grand cosmic puzzle, and each of us has a role to play in uncovering its secrets. So, as you look up at the night sky, remember this: the mysteries of the cosmos aren't just out there, they're within us, waiting to be discovered. Keep wondering, keep exploring, and never stop reaching for the stars. The universe is cosmic.